into a universe before memory. A cosmic ocean without stars, without gravity, without even the whisper of time. The narration lingers on a moment that is not a moment, a silence older than existence itself. A darkness so pure it feels like the void between thoughts. A place where the laws of physics have not yet been written, where even the concept of before collapses under its own weight. Out of this absolute stillness, something impossible happens. Space stretches from nothing. Time awakens. A boundary as thin as a quantum fluctuation becomes the birthplace of everything that will ever exist. The tone turns philosophical. What does it mean for the universe to begin? What machinery of nature ignites reality? And if beginnings are real, do endings wait at the far horizon? The camera drifts through the newborn cosmos. White-hot radiation, quantum storms, swirling primordial fields. A universe expanding faster than light, carrying the seeds of galaxies and the potential for consciousness across an infinite dark canvas. The narration introduces the central mystery, not just how the universe began, but what mechanism started this beginning, what existed before it, and how this same mechanism may dictate the universe's final fate. A final, trembling question closes the hook. If reality can emerge from emptiness, could it one day collapse into silence again? In the early years of the 20th century, when the night sky seemed eternal and unchanging, a quiet revolution began to take shape. Observatories perched on lonely mountaintops gathered the faint light of distant stars, and the mathematics of a young Albert Einstein reshaped the very geometry of reality. It was an era when the universe still felt infinite, ageless, and comfortably still, a cosmic stage assumed to have existed forever. Yet behind this illusion, the first tremors of a deeper truth were beginning to stir. Einstein's general theory of relativity, completed in 1915, carried within it a subtle but dangerous implication. Its equations did not easily permit a static cosmos. Spacetime, if shaped by matter and energy, should bend, sway, expand, or collapse under its own weight. The idea disturbed him. To rescue the universe from motion, he added a cosmological constant, a precise mathematical counterweight designed to force stillness upon a restless fabric. But the equations kept whispering the same warning. The universe wanted to move. Far above the haze of Los Angeles, atop Mount Wilson, a vast steel telescope watched the heavens with patient silver eyes. It was here, in 1929, that Edwin Hubble traced the faint fingerprints of distant galaxies across photographic plates. Their light, stretched by the fabric of space itself, carried a quiet confession. These galaxies were fleeing, drifting away on currents of expansion. The deeper the camera looked, the faster they seemed to retreat. Space was not static. It was swelling. The universe was growing in every direction. In that moment, the ancient belief in an eternal, unchanging cosmos fractured. If everything was moving apart, then at some unreachable point in the past, everything must have been closer together. A cosmic genealogy began to form, a vision of a universe seeded from a smaller, denser state, perhaps even a single catastrophic moment of birth. Yet this idea felt almost mythic, too audacious to be accepted without overwhelming proof. Evidence arrived not as theory or speculation, but as a whisper trapped in the sky itself. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were attempting to refine a microwave antenna at Bell Laboratories. They were not seeking cosmological revelation. They simply hoped to remove a persistent background noise, a faint, uniform hiss that would not go away. They cleaned the equipment. They recalibrated the instruments. They removed every possible source of local interference. Still, the sky hummed with a soft, ancient glow. Unbeknownst to them, theorists had predicted exactly this signal, the cooled afterlight of a primordial fireball, stretched into microwaves by billions of years of cosmic expansion. The universe, still warm from its earliest moments, had been carrying this echo across the void since time's first unfolding. Penzias and Wilson had stumbled upon the cosmic microwave background, a relic radiation older than any star, older than any galaxy, older than the very concept of structure. It was the universe remembering its childhood. Across the scientific community, the discovery hit with the force of revelation. The cosmos could no longer be imagined as eternal. It had once been incandescent, compressed into a radiant sea of particles. Hydrogen, helium, and traces of lithium, light elements whose abundances matched theoretical predictions, offered additional confirmation. The earliest structures of matter carried the proportions expected from a universe that expanded from an unimaginably small, hot, dense origin. The Big Bang model, once a daring speculation, began to crystallize into the most compelling narrative science had ever assembled. It explained the large-scale structure of galaxies. It accounted for the uniform temperature of distant regions of the sky, a puzzle later addressed by the inflationary epoch. It described the cosmic web stretching between clusters of galaxies, a frozen memory of density ripples imprinted in the universe's infancy. Yet beneath its triumph lay an unsettling truth. If the universe had a beginning, it meant time itself had a boundary. The cosmos was not an infinite backdrop upon which events unfolded. It was a story, a narrative with a first chapter written in radiation and quantum turbulence. As telescopes improved and detectors sifted through the background glow with finer precision, humanity glimpsed snapshots of the cosmos long before Earth formed, before the Milky Way's spiral arms unfurled, before stars lit their first fires. Satellites such as COBE, WMAP, and later Planck mapped the faint temperature ripples embedded in the microwave background, revealing the universe's earliest structure with exquisite detail. The patterns were not random. They were the fingerprints of primordial fluctuations, the seeds from which galaxies would someday grow. With every new dataset, the implications grew more profound. The cosmos did not simply exist. It evolved. It expanded. It cooled. It formed complexity out of chaos. And billions of years later, it produced observers capable of tracing its history back to that moment when space and time first awakened. The chapter of discovery, therefore, is not a tale of instruments alone. It is a shift in cosmic identity. Humanity, for the first time, understood that the universe had an origin. A point beyond which familiar physics dissolves into something stranger, something raw, something unbounded by the rules that govern stars and planets. A time when energy was everything and structure was nothing. This realization did more than reshape astronomy. It transformed the philosophical landscape. If the universe had a first moment, then the cosmos was not a quiet, eternal cathedral. It was a phenomenon, a process with direction, evolution, and perhaps an inevitable fate. The very fabric of reality carried the memory of its beginning, etched into radiation still drifting across intergalactic space. And so, the discovery era stands as a threshold in human understanding, the moment when the universe ceased to be a static backdrop and became a story with a first page. A story written in expanding space, ancient light, and the unbroken silence of cosmic time. A story still unfolding, still deepening, still guiding consciousness toward the mysteries that lie ahead. Across the vast silence of interstellar space, the camera drifts through the cold filaments of a distant nebula, a soft tapestry of stardust suspended in the dark. Light from young stars seeps through its swirling folds, illuminating pockets of gas where gravity has just begun its patient work. Yet beyond these delicate structures lies a deeper, more ancient question. If stars can be born from cloud and collapse, from swirling matter and turbulent pressure, then from what, if anything, was the universe itself born? For centuries, classical physics had whispered a comforting promise. The universe was eternal. Its laws were timeless. Matter and energy rearranged themselves in cyclical patterns, but the cosmic stage upon which they danced never changed. Time stretched infinitely backward, like a boundless sea with no visible shore. Nothing fundamental ever truly began. This assumption was not simply scientific, it was philosophical. An eternal universe required no genesis, no origin point, no boundary where the rules faltered. It was a cosmos that needed no explanation. But Einstein's general relativity had already introduced a quiet tremor beneath this certainty. His equations sketched a universe whose fabric could bend, stretch, or collapse under its own gravity. When solved honestly, without artificial stabilizers, the mathematics pointed toward an unsettling truth. The cosmos might have emerged from a state where the curvature of space-time rose without limit. A moment when density soared toward infinity. A singularity. The very word carried a sense of violation. The collapse of continuity, a point where the predictable scaffolding of classical physics simply failed. Infinite density. Infinite temperature. Infinite curvature. Space and time compressed into a dimensionless seed. Nothing in Newton's universe, nor in human intuition, could accommodate such a state. The camera moves deeper into intergalactic darkness now, where galaxies drift like ghostly islands. Their spirals rotate in slow cosmic ballet, but the void between them grows ever wider, the faint signature of expansion still written into the universe's bones. Expansion, if traced backward, does not dissolve into stability. It converges. And in that convergence lies the first shock. When Edwin Hubble observed galaxies receding, the implication was simple but devastating. If space is expanding today, it must have been smaller yesterday, smaller still the day before, and once, unimaginably, compressed into an almost inconceivable density. Scientists resisted this idea, not from stubbornness, but from a deep understanding of what it implied. A universe with a beginning, a universe emerging from a singularity, was a universe where the laws of classical physics, the bedrock of scientific certainty, no longer applied. Resistance crystallized into the steady-state model proposed by Bondi, Gould, and Hoyle. It was elegant, eternal, and philosophically comforting. In their vision, the universe expanded, yes, but new matter continuously formed to fill the growing void, keeping the cosmos uniform and unchanging on the largest scales. There was no beginning, no moment of creation, no singularity where physics broke down. The universe had always been, and always would be. For a time, this model offered refuge. But nature had already written its rebuttal across the sky. The cosmic microwave background, that faint, ancient radiation, lingered everywhere with perfect neutrality. A glow that no steady-state universe could produce. Its uniformity and precision erased the possibility of eternal stasis. And with each new measurement, a singular moment became harder to escape. The camera glides through a distant cluster of galaxies now, their halos glowing with dark matter's invisible pull. Gravitational lensing arcs light across the scene, bending it around mass as if space-time were a gentle ocean disturbed by unseen tides. This curvature, so beautifully predicted by Einstein, becomes more violent near greater densities. Follow it far enough back in time, and curvature does not merely intensify, it explodes. In the 1960s and 70s, Stephen Hawking and Roger Penrose formalized this brutal truth. Using the mathematics of relativity, they demonstrated that under reasonable physical conditions, matter obeying gravity, energy behaving normally, singularities were not optional. They were inevitable. If the universe is expanding now, then at some moment in its past, all geodesics converge. Space-time itself collapses into a boundary, a point where the equations cease to function. Beginning, they showed, is not a myth. It is the logical consequence of the universe's own evolution. Yet this revelation carried a secondary shock. If the Big Bang truly marked the origin of space-time, then time itself did not extend beyond that event. Asking what came before becomes akin to asking what lies north of the North Pole, a directional concept with no physical meaning. Reality had a cutoff, a point where classical causality simply dissolved. And with that dissolution came a profound psychological tremor. The universe, for the first time, seemed finite not in size, but in knowability. A frontier not of space, but of understanding. A boundary where human logic faltered. The camera sinks into a deep cosmic void where nothing stirs. No galaxies. No clusters. Only the thin whisper of stray photons crossing the abyss. Here, in this near-silent darkness, the emotional weight of the scientific shock becomes clearer. A universe with a beginning is a universe touched by mystery. A universe in which the ultimate origin may lie forever outside the reach of classical reasoning. Physics can describe the first trillionth of a second after the Big Bang, but as the clock winds further backward, the terrain becomes fractured. Quantum uncertainties dominate. Gravity and quantum fields merge into a domain for which no current theory can fully account. The singularity is not a physical point to be observed, but a symbolic marker where known laws shatter. Humanity stands on the edge of this conceptual chasm. Looking back into time, the universe appears increasingly compressed, increasingly chaotic, increasingly unknowable. At the very brink, knowledge itself evaporates. And yet, in this evaporation lies a strange beauty. The idea of a beginning implies that the cosmos is not infinite in its past. It is a phenomenon with an origin, a transition from a state beyond description into the structured universe observed today. It suggests that the deepest truths of existence may be rooted in laws more fundamental than relativity, more primal than the forces familiar to matter and light. It implies that physics is unfinished. There is vulnerability in this realization, a recognition that even the most powerful scientific frameworks crumble near the universe's birth. But there is wonder as well. If the cosmos emerged from a domain where classical logic breaks down, then its existence is not merely mechanical. It is emergent, contingent, astonishing. The camera rises out of the void and returns to the dense heart of a star-forming region. Dust glows in soft gold as gravity folds matter into spirals and whirls. Here, new suns prepare to ignite. Their light will someday drift across the galaxy, carrying within it the signature of thermonuclear fire. But beneath that fire lies the deeper memory encoded into every particle, a history that reaches back to the moment when all energy, all fields, all forces, all possibilities were compressed together. A moment when the universe began its long expansion from near-nothingness into immensity. This chapter marks the turning point in humanity's understanding, the realization that the universe did not always exist. That the cosmic story has a first line, one written in heat, curvature, and the collapse of classical certainty. A universe from nothing is not merely a scientific concept. It is a philosophical wound, a frontier of wonder, a reminder that existence itself is stranger, more fragile, and more temporary than the human mind was ever prepared to accept. The camera glides through a dark expanse, deeper than any night sky known to human eyes. Here, in the quiet between galaxies, ancient photons drift like tired travelers. They have been journeying for nearly 14 billion years, crossing the swelling fabric of space since the dawn of everything. They carry with them a memory, a soft whisper of heat from an age when the universe was young, blinding, and unbearably dense. These faint relics, stretched into microwaves by cosmic expansion, form the oldest light in existence. And hidden within their subtle patterns lies the story of creation itself. Humanity's attempt to read these patterns began with a single ambition: to unravel the conditions of the cosmos long before stars ignited, before galaxies swirled into their majestic forms, before light could travel freely. It required instruments that could drift above Earth's atmosphere, watching the sky with exquisite sensitivity, satellites designed not to see brightness, but to detect faint temperature variations measured in millionths of a degree. COBE, launched in 1989, was the first of these cosmic archaeologists. As it orbited high above Earth, it captured the microwave background with unprecedented clarity. What it revealed stunned cosmologists. The relic radiation was astonishingly uniform, yet not perfectly so. Tiny temperature fluctuations, mere ripples against a nearly smooth sea, emerged across the sky. These ripples were not noise. They were the earliest structures, the primordial seeds from which galaxies would someday grow. COBE transformed the cosmic microwave background from a mysterious glow into a structured tapestry, carrying the imprints of a universe only 380,000 years old. The camera descends into this tapestry now, revealing a mosaic of warm and cool regions scattered across the celestial sphere. Each region represents a density contrast, some slightly heavier, some slightly lighter. In the early universe, these contrasts acted as gravitational anchors. Where matter accumulated, future galaxies would form. Where matter was sparse, cosmic voids would stretch wide. WMAP followed in 2001, sharpening this picture. With far greater resolution, it mapped the temperature fluctuations with such precision that cosmologists could measure the universe's age, composition, and curvature. These fluctuations revealed a cosmos surprisingly flat, not curved like a closed sphere, nor bending open like a saddle, but nearly geometrically perfect. This flatness demanded an explanation, a mechanism that stretched spacetime so rapidly and uniformly that any curvature was smoothed into near perfection. The answer pointed toward a radical idea: cosmic inflation. Planck, launched in 2009, delivered the most detailed map of the microwave background ever recorded. Its sensors captured minuscule temperature differences across the sky, each a fossilizing echo of quantum fluctuations magnified by inflation's violent expansion. These fluctuations were once smaller than atoms, yet through cosmic inflation, they were stretched to astronomical scales, sculpting the distribution of galaxies across billions of light-years. As the camera weaves through vast clusters and filaments of galaxies, the viewer sees the scale of these ancient imprints, enormous walls of matter threading through the universe, separated by deep cosmic voids. This structure is not random. It carries the rhythmic signature of baryon acoustic oscillations, sound waves that rippled through the primordial plasma before the universe cooled enough for light to escape. These oscillations left behind a preferred scale, a faint but consistent spacing visible across the cosmic web. Every one of these patterns, temperature fluctuations, matter distribution, oscillation scales, points backward toward the first moments of cosmic time. They suggest a universe governed by physics so exotic, so extreme, that even the boldest theories struggle to describe it fully. The scene shifts, carrying the viewer to the heart of giant particle accelerators buried deep underground. Here, powerful magnets coil around circular tunnels, guiding protons to nearly the speed of light. When these particles collide, the energy momentarily recreates conditions reminiscent of the early universe, fleeting, microscopic echoes of the primordial fireball. Detectors record showers of subatomic particles as they burst into existence, providing clues to how matter behaved when the universe was younger than a trillionth of a second. Yet even the most powerful accelerators can only brush the surface of that early cosmic state. The energies achieved in these collisions represent a tiny fraction of those present during inflation or the earliest quantum epochs. What particle physics offers is not a full recreation, but a partial reflection, a glimpse of the processes that govern the universe's infancy. As the camera drifts upward through the accelerator halls, rising from the engineered caverns into the open night sky, the journey returns to the cosmic microwave background, the true archive of primordial history. Scientists analyze this ancient radiation not only for its temperature patterns, but for its polarization, the alignment of its light waves. These alignments trace the motion of electrons and photons during the earliest epochs, offering additional clues to the forces that shaped the universe's evolution. Certain features hint at the fingerprints of gravitational waves, ripples in spacetime produced by inflation itself. Though these primordial waves have not yet been definitively confirmed, their potential traces remain one of the most sought-after signatures in all of cosmology. They would offer direct evidence for inflation, revealing a universe once dominated by a mysterious energy field whose properties remain unknown. The camera floats through a deep cosmic void again, suspended in a region nearly free of galaxies. Here, the silence is profound. It is in places like this, where matter thins almost to nothing, that the cosmic microwave background appears clearest, unobstructed by galactic interference. From this vantage point, the universe feels less like a collection of stars and galaxies and more like a vast, evolving organism whose earliest memories lie encoded in ancient light. These clues collectively tell a deeper story. A story in which the universe's beginning was governed not by familiar physics, but by something more fundamental. A regime where quantum fields, vacuum energy, and space-time itself behaved with a freedom no longer visible in today's calmer cosmic era. They imply that the earliest moments of the universe were not simply hot or dense. They were different, governed by rules beyond the standard model, governed by energies beyond the reach of experiments, governed by a physics that shaped the universe long before atoms existed, long before light could travel, long before structure could form. The emotional undercurrent of this realization flows quietly beneath the scientific narrative. Every measurement, every fluctuation mapped by Planck, every particle tracked by accelerators, every oscillation traced through galaxy surveys, reminds humanity that the cosmos has hidden depths still far beyond understanding. The early universe is not merely distant in time. It is distant in nature, a domain where familiar logic breaks down, replaced by exotic states of matter and quantum fluctuations blooming into celestial structure. The chapter closes as the camera slowly pulls away from the primordial light, drifting outward through a sea of galaxies. Their shining forms feel fragile now, intricate snowflakes drifting through a universe whose earliest moments were violent, turbulent, and profoundly mysterious. Each star, each world, each filament of gas stands as a monument to forces unleashed at the very beginning. And within those faint microwave ripples, humanity reads not just a record of early structure, but a message. The origins of the universe are governed by a physics still beyond reach, still beyond comprehension, still waiting to be understood. In the vast silence between galaxies, where light stretches itself thin across expanding darkness, an unseen force moves with quiet certainty. It does not glow. It does not pull. It does not bend starlight or ripple space with the violence of collapsing suns. Instead, it acts with the gentlest of hands, yet its influence reshapes the destiny of all things. Across this cosmic dusk, the camera drifts beyond the last bright clusters, into a region where galaxies become solitary lanterns adrift in swelling night. Their motions whisper a secret. Space itself is speeding outward, lengthening the gulf between worlds, loosening the gravitational bonds that once held cosmic architecture together. It is here, in the growing stillness, that the first clues awaken. Every widening distance carries the echo of something profound, a force that accelerates expansion, a force older than structure, softer than gravity, stranger than any field ever proposed. This force will one day dissolve every familiar pattern: galaxies, clusters, superclusters, the vast filaments of the cosmic web. It will rewrite the ending of the universe long before the stars complete their final cycles. But its story begins in a moment of confusion, when humanity believed it understood the cosmic tale. When the universe's beginning seemed violent yet comprehensible, and its fate predictable. Then, in the final years of the 20th century, a discovery emerged that cracked open this certainty. A revelation arrived, subtle as dust, luminous as truth. The universe is not merely expanding, it is accelerating. And with that, the greatest deepening of the mystery began. The camera rises above the Milky Way, letting its spiral arms fade into a silver haze as the universe's larger terrain reveals itself. Vast regions of intergalactic darkness breathe like slow oceans, carrying galaxies outward along invisible currents. For most of modern cosmology, this outward drift seemed ordinary, a remnant of the primordial explosion that set everything in motion. Expansion was expected. Acceleration was impossible. Yet in 1998, two independent teams studying Type Ia supernovae uncovered a contradiction so immense that it overturned the foundational narrative of cosmic destiny. Type Ia supernovae, white dwarfs igniting in thermonuclear flame, possess a predictable brightness, a standard candle across billions of light years. By comparing their intrinsic luminosity to their apparent faintness, astronomers could measure vast cosmic distances with an elegance unparalleled in astrophysics. These stellar detonations served as markers, ancient mileposts scattered across the expanding fabric of spacetime. The teams expected distant supernovae to appear brighter than projections from simple expansion. Instead, they appeared inexplicably dim. The implication was unavoidable. They were farther away than the standard cosmological model allowed. Something was pushing them outward faster than gravity could restrain. Thus emerged a conclusion that shook cosmology to its core. The universe is accelerating. A force, repulsive, diffuse, omnipresent, pervades all spacetime. The camera sweeps across the large-scale cosmic web. Filaments shimmer like ancient highways of light, connecting clusters across tens of millions of light years. But faint ripples of accelerated expansion tug at these structures, stretching them ever so slightly, like threads on a loom pulled from its frame. Over cosmic time, this tension will grow stronger. This force is called dark energy, though the name reveals nothing. It is not energy in the familiar sense. It does not radiate. It does not concentrate. It remains the most elusive component of the cosmos, comprising nearly 70% of all existence, yet interacting with nothing except spacetime itself. Its simplest interpretation echoes Einstein's early intuition: the cosmological constant, an inherent, irreducible pressure embedded in the vacuum. Empty space, it seems, is not empty. Each cubic centimeter of vacuum contains a delicate whisper of expansive tension, a pressure so faint it cannot be felt within galaxies, yet so dominant that it shapes the universe as a whole. The camera glides through a region where galaxies drift like embers on an invisible wind. Their recession from one another grows swifter with increasing distance, as if the fabric between them thickens into something restless. Over tens of billions of years, this acceleration will overwhelm every gravitational bond that holds cosmic structure intact. But there is another, more speculative possibility. Perhaps dark energy is quintessence, a dynamic field evolving through time, waxing and waning as the universe grows older. This idea introduces motion where the cosmological constant offers stillness. A cosmic field rolling slowly down an ancient energy landscape, its behavior changing with the very expansion it drives. Each interpretation carries a different fate. If the cosmological constant rules, the universe drifts into a cold, eternal expansion, galaxies evaporating beyond one another's horizons. If quintessence dominates, the universe could accelerate more gently or tear itself apart. The camera descends toward a supermassive black hole at the core of a distant galaxy. Its accretion disk burns with ultraviolet fire, yet the galaxy around it shifts subtly outward. Dark energy cannot influence the black hole's immediate domain, but it surrounds it, presses upon it, and one day, will carry that galaxy into an isolation so complete that even neighboring clusters become unreachable. This acceleration alters not only the universe's end, it reshapes our understanding of its beginning. The equations of expansion link present behavior to ancient conditions. If expansion is accelerating now, then its earliest moments hold deeper mysteries than once assumed. The energy field driving cosmic acceleration today may be faint residue of a primordial force. The very field that powered inflation. Inflation, that fleeting era when the universe expanded faster than light, left fingerprints in the cosmic microwave background. It smoothed the universe, flattened it, gave rise to quantum ripples that later became galaxies. Dark energy, though billions of times weaker, echoes inflation's nature. A quiet symmetry, the universe's first expansion may be whispering still. Thus emerges a profound suggestion. The beginning and the end may be governed by the same underlying physics. Two eras of expansion, divided by billions of years, driven by fields that inhabit the vacuum itself. The camera now travels to the edges of the cosmic horizon, where light from ancient galaxies stretches into thin, red filaments. These galaxies, once neighbors, will eventually slip away faster than light can bridge the gulf. They will fade not because they die, but because they become unreachable, lost beyond the cosmic event horizon defined by acceleration. This is the loneliness dark energy brings. The universe grows quieter, emptier, more isolated with time. Yet within this loneliness lies philosophical weight. For a universe that accelerates must be examined differently than a universe that coasts. Its structure becomes temporary. Its future becomes fragile. Its beginning becomes more mysterious. Dark energy suggests that the universe's very fabric, the vacuum beneath all particles, fields, and forces, is not fixed, but active. The classical view of emptiness dissolves. Space is no longer a stage. It is a participant. This realization deepens the enigma of origins. If vacuum energy can drive expansion now, what might it have done when the universe was smaller, hotter, more violently curved? If cosmic acceleration emerges from quantum fields, then the first moments of existence must be governed by physics beyond the reach of present theories. Dark energy does not simply accelerate the universe. It accelerates the mystery. The camera withdraws from the cosmic horizon, returning to the familiar swirl of the Milky Way. Yet even here, dark energy whispers, a faint reminder that everything from star clusters to cosmic webs floats on an ever-stretching sea. Humanity once believed it had approximated the universe's blueprint. But the discovery of dark energy revealed a truth both humbling and beautiful. The cosmos is stranger, quieter, and more unknowable than imagination alone could conceive, shaped by a force that may connect its birth to its inevitable fading. The mystery deepens, and the journey to its source grows darker still. Across the vast corridors of intergalactic darkness, where the last starlight drifts like aging embers, the universe carries within it a set of fates, silent, immense, and utterly indifferent. These futures are not prophecies, but possibilities. Each one rises from the same ancient equations that describe how galaxies move, how matter cools, how space-time curves beneath the weight of creation. As the camera glides through a dim, fading cluster, its remaining suns flicker with the quiet exhaustion of cosmic age. Their light spills across an ever-expanding void, stretched thin by a force that does not sleep. Here, space grows colder, smoother, emptier with every heartbeat of cosmic time. Yet from these distant landscapes emerges a question older than philosophy itself. How does a universe end? In the ruins of collapsed stars and the stillness of darkened nebulae lies a tension between inevitability and uncertainty. The cosmos offers many endings, some gentle, some violent, some cyclical, some absolute. Each one unfolds like a final chapter written in a language of entropy, geometry, and quantum possibility. There is the slow extinction of all energy, the catastrophic unraveling of matter, the crushing collapse of space-time back into primordial fire, the eternal rebirth of cosmic cycles, and the sudden rewriting of existence by a deeper vacuum. The universe hides these futures in the faint patterns of its expansion and in the trembling fields beneath reality itself. And as the camera drifts deeper into the abyss, past the thresholds where galaxies vanish into darkness, an existential truth emerges. The end of the universe is not a distant myth. It is a scientific question, waiting in the quiet hum of space-time. The camera opens on a lonely galaxy drifting through expanding void, its spiral arms stretched thin by cosmic aging. Dark halos shimmer faintly like the fading memories of clustered matter. This is the natural stage on which the first great ending unfolds. The heat death. 1. Heat death/big freeze. In this vision, dark energy continues its silent acceleration. Galaxies drift apart until light itself becomes a private property of isolated islands. The cosmic web loosens. Filaments thin. Clusters detach into solitary realms. Within galaxies, star formation dwindles as cold gas runs out. The last red dwarfs burn dimly for trillions of years before finally fading into black cinders. White dwarfs cool into black dwarfs. Neutron stars erode through proton decay. Black holes, once titanic engines of infalling fire, seep energy through Hawking radiation, evaporating slowly into faint whispers of annihilated curvature. As entropy increases, usable energy disappears. Temperature balances into near absolute zero. No gradients remain. No motion can be exploited. A universe without free energy is a universe without change. The camera drifts across this silent expanse. Nothing stirs. Nothing glows. Every structure has dissolved into a dilute ocean of particles spread thin across eternal expansion. This is not destruction. It is exhaustion. A cosmic winter in which time continues, but meaning does not. 2. Big rip. The camera abruptly shifts. Space-time begins to tremble. Distances lengthen faster. Galaxies stretch. Their gravitational anchors weaken. This is the second fate. The Big Rip, governed by phantom dark energy, a form of dark energy whose density grows as the universe expands. Instead of thinning, it strengthens. If phantom energy dominates, there will come a moment when even the Milky Way cannot hold itself together. Stars drift from stars. Planets lose their orbits. The solar system unravels. The acceleration intensifies. Galaxy clusters dissolve. Galaxies shred. Stars tear apart. Planets rupture. Atoms stretch. Even subatomic structures feel the strain of expanding spacetime. Moments before the end, the camera hovers above a lone particle. It vibrates as the fabric supporting its existence begins to fail. Then spacetime, under infinite expansion, fractures. The universe ends not in cold darkness, but in an explosive unbinding of everything: matter, forces, fields, geometry, ripped apart in finite time. 3. Big crunch. But the camera suddenly reverses direction. Expansion slows. Galaxies no longer flee. Their recession pauses as if the universe takes a deep breath. This is the big crunch, a fate in which dark energy weakens or reverses, allowing gravity to reclaim dominance. The universe halts its outward rush and then collapses inward. Galaxies begin converging. Clusters merge into titanic structures glowing with the fires of renewed star formation. Temperatures rise as compression builds. Background radiation grows hotter. The camera moves inward through tightening filaments, as if the entire cosmic web is folding into itself. As collapse accelerates, matter crowds into smaller and smaller volumes. Curvature increases beyond comprehension. Every region brightens into blinding heat. The universe becomes a furnace, returning to conditions reminiscent of its earliest moments. At the final instant, all matter, all space-time, all energy compress into an ultra-dense cosmic ember. It is the inverse of expansion, a universe collapsing toward singularity. Whether this singularity marks annihilation or transformation remains unknown. For the big bounce. But from the ashes of collapse comes a different possibility. Quantum gravity theories, loop quantum gravity, string cosmology, and others propose mechanisms that prevent true singularities. Space-time, at its deepest scale, may have structure, granularity, or quantum tension that halts collapse before reaching infinite density. In this view, the universe does not end in a point. It rebounds. The camera moves inward until it meets a shimmering boundary, a quantum horizon beyond which classical geometry cannot proceed. Pressure reverses. Contraction transforms into expansion. A new universe blossoms from the compressed seed of the old. Not a single event, but a cycle. A cosmic heartbeat echoing across eons. Each cycle might alter the constants of nature, restructure cosmic laws, imprint new patterns onto the fabric of reality. The familiar might dissolve, replaced by universes with different physics, different structures, different destinies. In the Big Bounce, the end is never final. It is transition. 5. Vacuum decay. Then the camera enters the most unsettling terrain of all. Not cosmic exhaustion, not collapse, not cycles, but transformation at the most fundamental level. A field permeates all reality, the Higgs field, whose value gives particles mass. If this field sits in a false minimum, a metastable state, then the universe may not be in its true ground state. In this scenario, quantum tunneling could trigger a vacuum decay event. A lower energy vacuum bubble could form somewhere in the universe. It would expand at nearly the speed of light, rewriting physical laws as it grows. No warning, no resistance, no survival. Inside the bubble, particles would have different masses. Atoms might not form. Chemistry could disappear. Space and time could obey new equations. The constants that structure matter would shift into an unfamiliar configuration. This is not destruction, it is replacement. Reality overwritten by a more stable version of itself. The camera approaches a theoretical bubble wall, a faint, expanding sphere of altered vacuum. Outside, physics behaves as expected. Inside, everything is different. A universe with new rules expands through the old. Humans could never see it coming. The event horizon arrives faster than awareness. This possibility carries a quiet, existential terror. The universe appears stable, yet deep beneath the fabric of space-time lies the chance that it is balanced on an unstable plateau. The cosmos could already be rewriting itself somewhere beyond our horizon. Closing reflection. As the camera drifts back into the interstellar dark, each ending lingers like a distant echo of possibility. Some are gentle, some violent, some cyclical, some absolute, and some occur not in the future, but in the very fields that define the present. The universe carries many deaths within it, but among them lies a deeper truth. To understand how everything ends is to understand why anything exists at all. The journey continues, into deeper mysteries still. Across the silent gulf of intergalactic night, an array of instruments points upward, sleek observatories orbiting above the atmosphere, crystalline mirrors nested inside spaceborne machines, radio dishes spread across continents like metallic constellations. They are the senses of a species seeking to understand the vast machinery into which it was born. Through these instruments, the universe is no longer merely watched. It is interrogated, measured, and compared against the quiet logic inscribed in its earliest light. The camera drifts past the gleaming sunshield of a space telescope, its gold-coated mirrors reflecting the pale glow of distant galaxies stretched by cosmic time. Far below, Earth rotates with steady indifference, unaware that its instruments listen to murmurs older than its continents, older than its oceans, older than its sky. In this age, cosmology is no longer a story told in theories alone. It is a story carved out of photons, neutrinos, gravitational waves, and particles colliding at the edge of human engineering. Each observation carries a fragment of the universe's memory, the residue of inflation, the drift of galaxies, the rhythm of expansion, the trembling energy of quantum fields. But these tools do more than look back. They peer forward, searching for signs of the universe's ultimate direction, toward cold silence, violent rupture, collapse, or rebirth. In their sensors and simulations, a profound question resounds. Can the fate of everything be read in the universe's earliest whispers? And as the camera pulls away from Earth's orbit, its gaze expands into the void where telescopes hover like lanterns in ancient darkness, illuminating not just what the universe was, but what it is becoming. The chapter opens on the James Webb Space Telescope drifting through Lagrange Point 2, a silent outpost beyond Earth's shadow. Its honeycomb mirror, glowing faintly gold, reflects the stretched halos of primordial galaxies. JWST is more than an observatory. It is a time machine reaching back to the universe's first few 100 million years, where infant stars ignite and the faint scaffolding of cosmic structure forms. 1. Telescopes searching for clues in expansion. The camera glides outward from JWST to the distant shape of the Euclid spacecraft. Its instruments measure the geometry of the cosmos with exquisite precision, mapping how galaxies cluster across billions of light years. By studying weak gravitational lensing, the minute distortion of distant light by dark matter, Euclid reconstructs the cosmic web like an archaeologist surveying ancient ruins. Nearby in future spaceflight, the Roman Space Telescope extends this effort with a field of view hundreds of times larger than Hubble's, capturing vast stretches of sky in single exposures. Its surveys aim to dissect the nature of dark energy by charting how cosmic expansion has changed over time. On Earth, the square-kilometer array stretches across deserts and horizons. It listens to hydrogen whispers drifting from the young universe, tracing the evolution of cosmic structure from the first billion years to the present. Through radio waves, it reveals forms of matter invisible to optical eyes, structures defined not by light, but by gravity. Combined, these observatories offer a panoramic portrait of cosmic expansion, its rate, its acceleration, its potential evolution. They form the foundation on which predictions of the universe's fate are built. 2. Particle colliders probing the Higgs field. The camera transitions from cosmic scale into the subterranean expanse of a particle collider. Superconducting magnets accelerate protons to near-light speeds, and the detectors at collision points flash with bursts of energy resembling miniature stars. This realm seeks answers in the stability of the Higgs field, a field that permeates all space and gives particles mass. Should this field sit in a metastable state, the universe carries a potential instability buried deep within its quantum fabric. Experiments at the Large Hadron Collider and proposals for next-generation colliders attempt to measure the Higgs boson's self-interaction with enough precision to determine whether vacuum decay is a distant threat or an improbability. These measurements are not simply about particles. They are about the durability of existence itself. The camera zooms through the collider's magnetic rings as if following protons racing toward collision. Sparks of energy bloom like microcosmic explosions. Within these ephemeral flashes, the universe reenacts conditions akin to its first trillionth of a second, in hopes of revealing whether its foundations are secure or poised on a fragile threshold. 3. Gravitational wave observatories listening to early physics. Next, the camera drifts toward the long arms of a gravitational wave observatory. Laser beams travel kilometers down vacuum tubes, their reflections trembling with exquisite sensitivity to ripples in spacetime. These observatories, working in concert across Earth and in spaceborne missions planned for the coming decades, listen for gravitational waves not only from black hole mergers, but from the earliest moments of cosmic time. A primordial gravitational wave background may carry the imprint of inflation, the universe's brief, exponential expansion. Such waves, if detected, could reveal the physics that shaped the universe before any atom existed. They might distinguish between different theories of inflation, or even point toward new fields, new symmetries, or the fingerprints of quantum gravity. The camera drifts along a laser beam as it splits, reflects, recombines, its interference pattern trembling with the quiet murmur of warped spacetime. For mapping dark matter through weak lensing. From the sterile hallways of observatories, the scene shifts to the cosmic web itself. Filaments stretch like luminous rivers across the void. Galaxies cluster along these invisible structures, guided by the gravity of dark matter. Weak lensing measurements from Euclid, Roman, SK, and observatories on Earth reconstruct this web with unprecedented detail. The distortions are subtle, fractions of a percent, but collectively they reveal the slow evolution of matter across cosmic time. By comparing observed structure to theoretical models, cosmologists test how dark energy shapes the growth of cosmic architecture. If the rate of structure formation drifts from predictions, it could signal time-varying dark energy, modifications of gravity, or new physics operating across the cosmos. The camera glides through a simulated filament, weaving between glowing galaxies suspended like beads on an invisible string. Their arrangement whispers stories of the universe's long-term trajectory. 5. Simulations predicting cosmic futures. On digital landscapes inside supercomputers, universes evolve at accelerated speeds. Simulations like Illustris, Eagle, and Millennium TNG model billions of years of cosmic history and project billions more. These vast virtual universes integrate dark matter dynamics, gas cooling, star formation, black hole feedback, gravitational collapse, and cosmic expansion. By adjusting cosmological parameters, dark energy density, matter density, curvature, and physics beyond the standard model, researchers test how different assumptions alter the universe's fate. Some simulations show galaxies fading into isolation. Others reveal rapid disintegration from extreme dark energy. Some see cycles of collapse and rebound. Others introduce quantum gravity corrections that alter the very fabric of spacetime. The camera roams through a simulation's data field. Galaxies flicker into existence, merge, stretch apart, and dissolve. It is a theater of possibilities, revealing futures shaped by physics yet to be discovered. 6. Missions studying time variation of dark energy. A subtler frontier emerges in the search for time-dependent dark energy. Missions such as Roman and Euclid analyze standard candles, standard rulers, and large-scale structure to test whether dark energy strength is constant or changing. If dark energy evolves over time, it might merge early universe physics with final universe destinies. A decaying field might lead to a slowing of expansion. A strengthening field might signal a big rip. A field oscillating between phases could point towards cyclic cosmologies. The camera moves through plots of expansion histories, each line reflecting a possible rhythm of cosmic evolution. The future becomes a branching tree of outcomes, each limb determined by the unseen behavior of a pervasive, mysterious force. Closing reflection. As the chapter ends, The camera withdraws once more into interstellar quiet. Telescopes hover like sentinels in the void. Simulations churn in the darkness of supercomputers. Lasers hum across gravitational wave arms. Colliders crack open the quantum depths of reality. These tools stretch across scales, from the largest cosmic webs to the smallest quantum vibrations. Together, they pursue one profound goal: to read the universe's fate in the faint imprints of its birth. In their data and silence, a truth emerges. To understand how everything ends, science must first understand how everything began. In the faintest hours of cosmic memory, before any star carved light into the void, there existed a silence so absolute that even time hesitated to begin. It was a stillness without shape or temperature, a waiting vast enough to hold the possibility of everything and the certainty of nothing. In that ancient hush, the universe balanced on the razor's edge between existence and absence, as if the cosmos itself was taking a single quiet breath before stepping into eternity. Now, billions of years later, that first breath echoes across the stars, soft, stretched, diluted by distance, yet still carrying the signature of its origin. The universe expands like an exhalation, drifting outward through cold and uncharted space. Every galaxy becomes a fleck of cosmic dust suspended in an ever-widening tide, each one a reminder of a moment when nothing surrendered to something. And in this late age of starlight, another silence slowly gathers on the horizon. A silence not of beginnings, but of endings. It waits in the far future, patient and inevitable, shaped by the same physical laws that once ignited the heavens. The symmetry is unmistakable. The cosmos began in a silence it did not understand. And one day, it may return to a silence it cannot prevent. Between those two stillnesses lies everything: the rise of galaxies, the birth of planets, the fragile spark of life, and the fleeting awareness of a species capable of contemplating the arc of creation itself. And so, the story of the universe becomes a circle drawn across unimaginable time, where the beginning gently mirrors the end. The camera drifts through the dim corridors between galaxy clusters, moving through a cosmic architecture thinning with age. Stars burn with a gentler glow here, as though aware that the grand furnace of existence has already passed its peak. In this late epoch of the cosmos, everything luminous carries a faint whisper: all things that begin must one day fade. The universe, once young and fierce, now expands like the slow release of a breath held for too long. It is a gesture written in its earliest equations: the stretching of space, the cooling of matter, the widening gulf between all points. From the birth of the first atoms to the drifting of the last galaxies, the cosmos behaves like a single cosmic respiration: inhalation at the Big Bang, exhalation across the eons. Nebulae curl like evaporating smoke. Supernova remnants fade into transparent lace. Even the Milky Way, grand spiral of 100 billion suns, traces its path toward collision, transformation, dissolution. Fragility is not the exception. It is the rule written into the fabric of reality. Yet fragility gives shape to beauty. The camera sinks into the ghost-pale arms of a stellar nursery, a world of gas, dust, and quiet radiance. Here, new stars ignite with the same fire that once illuminated the infant universe. The process is ancient, familiar, almost sacred. Gravity gathers, pressure rises, fusion awakens. Light blooms. And for a brief chapter in an endless story, brilliance pushes back the darkness. But even these newborn stars are temporary visitors. Their light, no matter how radiant, is finite. Their warmth, no matter how generous, will one day fail. The cosmos writes its story in eras, not eternities. Beyond these clouds, deeper still into intergalactic night, the film drifts toward the universe's far horizon, a boundary not of distance, but of time itself. The photons reaching this distant edge are among the oldest travelers in existence, relics from when the universe was scarcely a few 100,000 years old. Their faint warmth, the cosmic microwave background, is the fossil imprint of the first breath of creation. Here, the chapter loops back on itself. The beginning mirrors the end because both are governed by the same relentless physics: expansion, entropy, cooling, dispersal. The laws that once coaxed galaxies into existence will one day unweave them. Gravity builds, time erases. It is an ancient rhythm, older than stars, older than atoms, older than structure itself. And within this rhythm lies a subtle, haunting paradox. The temporary nature of everything, stars, planets, oceans, civilizations, is what makes their existence meaningful. Permanence would dull significance. A universe where nothing changes would also be a universe where nothing matters. But this universe evolves. It ages. It ends. And in doing so, it creates moments of astonishing beauty that would otherwise never appear. The camera glides across a quiet exoplanet orbiting a red dwarf, a world bathed in soft, amber-colored light. Waves roll against frozen shores. Winds trace patterns across ancient dunes. Here, time stretches like cold syrup, slow and delicate. The star above will burn for trillions of years, long after all brighter suns have collapsed into embers. Yet even this enduring world cannot escape the universe's eventual fate. It merely lingers near the outskirts of time. From this silent world, the perspective rises outward, climbing through interstellar emptiness until galaxies shrink into a faint web of light. The cosmic structure, filaments, nodes, voids, resembles a vast nervous system flickering across a godlike scale. It is a design sculpted by dark matter, refined by gravity, illuminated by stars. But even this great cosmic web is temporary. As dark energy accelerates expansion, the filaments stretch, loosen, dissolve. Galaxies drift beyond each other's reach. The universe becomes a collection of lonely islands surrounded by deepening night. In the far future, silence returns. This silence, however, is not the quiet before existence, but the quiet after creation's long exhalation has finished. A silence not empty, but exhausted. A silence shaped by the final glowing remnants of a universe that once blazed with a trillion suns. Yet in this contemplation of endings, an unexpected thought emerges like a flicker in the dark. If the universe began once, might it begin again? If existence can erupt from a state where time does not flow, could such a spark repeat? Is the end a conclusion, or merely the border of a larger, unseen pattern? Some cosmological models whisper of cycles, where universes expand, cool, collapse, and ignite anew. Others speak of quantum fluctuations seeding new realities in an eternal cosmic sea. None are proven. All remain distant hypotheses. But each suggests a deeper truth. The universe may not merely end, but transform. If creation is possible once, why not again? The camera pulls back until even galaxy clusters vanish, leaving only a dim haze of cosmic structure evaporating into the abyss. Here, at the conceptual end of time, the universe resembles its earliest moments. Cold, simple, silent. The loop closes. The circle completes itself. The beginning reflects the end becomes a mirror to the beginning. And within this vast sweep of cosmic history, a singular, fragile phenomenon stands apart: consciousness. For a brief interval, a sliver of time so thin it barely registers on cosmic scales, the universe produced beings capable of recognizing its own story. Stars formed atoms, atoms formed molecules, molecules formed minds. And those minds looked out into the darkness and realized they were part of something immeasurably greater. A universe that can be understood is a universe that, in some quiet way, becomes alive through the act of understanding. The camera returns to the cosmic void, now serene and infinite. The final image lingers on the faint glow of receding galaxies, drifting toward destinies shaped by physics older than time. A universe vast beyond imagination, illuminated, briefly, by minds capable of understanding it. If you felt the journey of this final chapter, then subscribe, like, and join the Science Scroll channel, where the universe meets imagination, one cosmic breath at a time.